Okay. Cool. Yeah. Hello, everyone. Welcome to Paper Club. Um, Today we're going to discuss about this paper called Titans: Learning to Memorize at Test Time. It's a paper from Google Research. I picked this paper. Well, actually, it's one of the paper Peter suggested to me, and I think it can make um the new trend in the research to handle like this long context sequence, and I've seen it's quite famous in the community at the moment, so I thought it's a good paper to discuss at paper club. Yeah, okay, so to start with, what actually the current problem that this paper is addressing? So this paper basically is talking about the problem we have with the most common architectures in handling like long sequence modeling, like transformers. Um, just to like a little bit of recap with transformers. So with transformers, basically we use this normally in like long like sequence, and then we have this attention mechanism in transformers where we attend to every token in that sequence. So what I mean by attend is that we want to see like every token compared to other token. And as we can imagine, if we have like really long sequence, that this process will be like, it will scale up really huge. Like it has quadratic complexity, like O(n) square. Um, this means that we cannot easily scale up this approach of these traditional transformers to really long sequence. Separately, there are also like older approach to this, which is like RNNs, recurrent neural networks, where we have like a fixed window, means that we have like a fixed context length, blow up the memory like in transformers, but we are limited to that context length. So if there is important information that is way too long in the past, like outside the context window, then the model will not be able to see. So basically, this is the problem that this paper is addressing, that basically how can we still incorporate information that exists in the long past of the sequence, but it doesn't like blow up the memory when we scale up. Yeah, and related to what the trend in the industry right now with the LLMs and the long text. So I think it's something like interesting to look into. Uh, okay. What's the next point? So, okay, in very general, what does this Titans offer? We will dig into more details about it, but long story short, summarized, these Titans, basically it introduced a separate module called like neural module memory, separate from the main uh, architectures. And then this neural memory, basically it can learn at task time, meaning that the information in this memory is always updated. So tying back to the problem that this paper addresses, that we want to be able to incorporate information from long past history, and we also want to be able to always update this memory when we see new data during inference. And what I mean by during inference here is that when we use this model to like read a long sequence of text during test time, this text that the model sees during test time will be used to update the memory in this neural memory module. So that's the idea. They also mentioned that another contribution is about the parallelization in the training. So because we can imagine with like sequence modeling, if we do like very sequentially, then it will take too long to run the training and inference, and they have also like separate section about how they can parallelize this. And the last thing, which I think is also very important, is that how this separate neural memory module behave with the main architectures. Okay, so to make it clear, this paper is basically introduce an extra, like separate memory module that will interact with the main uh, transformer or the main attention modules in the whole system. So it's very important also this paper discuss about how the separate neural memory module interact with the rest of the architectures. Okay. Um, yeah, a little bit of introduction or like related studies. As I mentioned before, a problem with transformers is that the quadratic complexity or n square, and it will make it really severe with long sequence. A lot of other studies before solve this problem by linearizing transformers, but based on the performance, like they mentioned here that it's not as good as the original transformers. Uh, so yeah, like this is like one thing that I want to uh sell here. Like this Titans performs better than the original transformers, so it doesn't sacrifice that performance. Okay, let me see what's the next point. So stepping back a bit, like what inspired the design of this Titans? So basically, this paper also discuss about what is actually a memory and how does memory work in the regime of like neural in machine learning. So basically, like memory is a, like something where, how to say, like they mentioned like here, learning is basically a process of retrieving information from memory and also update the memory. So this process of retrieving information and updating the memory, it's like a continuous process that needs to happen. Uh, and that's why it's so important to be able to do this in the test time as well, because we might, the system might see new information that is beneficial for the memory. So this is something that they really emphasize in this paper. And this concept of memory, meaning that retrieving information and updating the memory, is actually implemented in those other like sequence modeling like transformers and RNNs. It's just the difference between these architectures is like how the process and like how the memory is stored, like in what sort of form. Like for example, in transformers, the memory is basically a collection of key and value metrics. So during the inference, like the the text that it sees will become like a query, and then it checks in the memory using which key is the most similar to the query, meaning like which part of the memory is the most similar to the question or the text that we want to see, and then the memory will check, oh, what is the value of that key. So it has some like this mapping between key and values, and then the process is basically find which key is the most similar to query. And same wise, during the updating process, is just basically uh, updates the memory by adding more key and value pairs. So yeah, this is like the implementation of the concept of memory. I think they also mentioned, yeah, with RNNs. Yeah, with RNNs. In RNNs, we know the concept of hidden states. And these hidden states basically acts as the memory. So every time it reads through the sentence, then this hidden states like captures the information of that sentence. So it means that hidden states acts as the memory. The difference between the RNNs and transformers is that with RNNs, um, the length of the how to say, like, the size of the memory is fixed because RNN has like a fixed context window. So it, like, if we scans through the sentence, then at some point we will forget the password. For transformers, there is no such a thing like this, and it keeps growing. So yeah, and then this paper is basically stepping back from that. So if all of these existing architectures basically use the same concept of memory, but just different way of updating and retrieving information in like different way of format and size. So they have these five questions, which I think are like a really good process, like thinking process to develop this research. Is like, first, what constitutes a good structure for the memory? Secondly, what is a proper memory update mechanism? What is a good memory retrieval process? And like very specific towards this paper is that how to design an efficient architecture that incorporates different interconnected memory modules. And last thing is that is a deep memory module needed to effectively store or remember long past. Okay. Um yeah, so in this thing, as I mentioned before, they introduced this a separate neural, what they call long-term memory. And why they call it long-term memory is that because it's sort of like compress the information from long past history, and it has the capability to filter out, like, if new information that it sees is surprising, like it's a new information, like put it in the memory. And it also has some mechanism to know what to forget. So it means that we keep very important information, but we don't like blow up the memory. So that's the key they want to introduce here. We don't want to blow up the memory like transformers, but we want to keep important information. um yeah. Yeah, okay. And then the next bit about the architectures, which they also heavily emphasize here. So I think there was section. Okay. So they are also basically inspired by how human brain works. Like, they believe that there must be a like separate different modules, like different systems in humans brain that work together to perform like the whole memory system. So it's not like one single system that can like compress and process all of the information as like one singular memory module, but there should be like different, like various a memory module that works together somehow. And they separate it into, first, the what they call short-term memory. So this short-term memory, the job is basically to process like new information. And this architectures is basically the core, the main attention system, the main attention modules. So that's why they say it's responsible for the main flow of processing the data. And because it's short-term memory, then it has limited window size. Um, and the second memory module is the long-term memory. So, so this is the module that they introduce here as Titans. And the job of this long-term memory module is that to store long past information. And as mentioned before, because it's long past information, it needs to have some mechanism to know what information is important to keep and what to forget. And the third bit they mentioned here is another module called like persistent memory. I don't think they really dig deep into persistent memory in this paper, but basically the idea is that there must be a certain set of knowledge about a particular task, and this is independent from the incoming data. So whatever the model sees during the test time, whether for like new words or new information that it sees, that this persistent memory stays the same because it has like the core fundamental knowledge about a task. So yeah, this is like three different memory modules that they believe is very important to make up a good memory system. And these three modules should be able to operate independently, but then they interact with each other. And we will see later that this core or the short-term memory is something that they train during training time, but not at the test time. But the long-term memory is trained during both training and test time. It means that if we receive new information during test time, that this long-term memory will be able to learn and update like the weights basically. Okay, and yeah, they evaluated on a lot of tasks. I'm not going to talk deeper about the experiments because honestly, they mention like everything in all tasks, like their architecture performed the best. um, and yeah, it's like a lot of experiments. So I think it's more interesting to know how they approach the architectures and how they are fit into the whole architectures. Okay. Yeah, this one is just a recap of it. So we will see. Yeah, this long-term memory. Okay, so let's go into the details of this long-term memory. Yeah, to recap again, that they argued that we need to have in addition to the core attention short-term memory, we need to have a separate online meta learning model that is also learning during test time. Like it's my first time to read about this meta learning. Yeah, so I find it interesting. They also argue that it's sometimes it's like a bit scary that we have something that memorize data, because memorize is sort of like the opposite of generalization, and we want our models normally to be able to generalize instead of memorize. But they argue that if we have a model that can learn during test time, like what to memorize, what not to memorize, then it will make better performance. So okay, so how does the learning process work in this long-term memory? So basically, again, the idea is that we want to be able to compress information because we don't want to block the memory, and we want to know which information to store and which information to forget. And how do we know this? They have this term called surprise. So surprise means that like how new the information compared to what the model already has. So how they calculate surprise is basically calculating the gradient with the respect to the input. The higher the gradient is means that the more the input, and then the more we want to keep the information. But as we can imagine, like just imagine as a human, if we read something new, if we learn something new or read something new in the news, and then oh yeah, this is a new information, and then we will like okay, because this is new, this information like is stick in our brain because it's new. But then after a certain amount of time, if we keep reading this yeah kind of similar information or similar news, then this is not like adding more in our brain, because like the degree of new is like become smaller and smaller. So in this situation, like back to the model, is like the gradient of um the new information with the model becomes smaller, and then at some point it will be like zero, like vanish. And then basically the model will not learn that the new information like the model will not be able to learn new information, because then the model sees everything as something not new. And it's kind of similar to the concept of gradient descent with momentum. So just a little bit of recap, like in like traditional machine learning, when we train with gradient descent, the idea is that we want to go down the loss function. So if like we want to find which path has the biggest gradient, like which path has the most steep to go down the loss function. But at some point, when the path becomes like a bit flat, like plateau, then the model like doesn't learn anymore. It stops learning, although it has not reached the global minima. Just because there is like a saddle or like plateau point, then the model stops learning. And how we have been addressing that problem in uh, deep learning training is that we add this momentum term. The idea of momentum is that we want to take into account a few past gradients instead of the gradient of that particular time. So in that situation, even though the model starts to learn like going down the loss function and then it reach a plateau, then the model can still see, oh, I've been going down for the past few steps, then I still need to like go further instead of just stop, compared to if the model only sees the current gradient, which is like zero in the plateau section of the loss function. So that is kind of similar to the problem we have here. Like if the information is seen like few times, then there is no surprise effect, and then the model stops learning. So they have this um, past surprise element like component of this equation that basically resembles momentum, so that we still want to incorporate like a few past surprise as well as the current surprise, which is like the new information that the model sees. Okay, and this eta, okay, I hope I say uh, this symbol correctly. This eta is basically represents like how much we want to incorporate this past surprise, past recent surprise. I would say this because it's past, but we it's not like long past, but it's like recent past. How much we want to incorporate this in the loss function, and this theta is basically the learning rate of like how much we learn from the momentary surprise. Um, yeah, okay. So this is how they train it. It's basically similar to gradient descent with momentum. Uh, and yeah, and I guess like this eta is like hyperparameter. I'm not sure whether this eta is something that the model learns or is that hyperparameter. Like whether we need to define. Oh, I want to completely forget the the past surprise. Just want to incorporate the
I think
current.
it is something that the model learns. It's
Yeah.
a it's like the outer one of the outer loop weights of the meta learning algorithm.
Yeah. Okay. Yeah. Yeah. Okay. Makes sense. Okay. So that's the inner loop and outer loop. Yeah. Okay. So anyway, I talked to Peter yesterday, which I think I also want to share here for people who are not familiar with meta learning. That there are terms called inner loop and outer loop. Like what are that? What are they? So inner loop is basically the process of the training of this in this context, in this paper context, is the process of the training of this separate long-term memory module. And the outer loop is the training of the main core attention modules. And basically, the during the training time, both inner loop and outer loop are like training because we want to update the weights of the long-term memory module during the inner loop training, but we also then want to update the weights of the main uh, attention modules. But during test time, this is why we this is called like test time training. Is during the test time, the inner loop is the only one that trains, which is this long-term memory module. So the weights of that long-term memory module is updated during test time, but not the attention. And then there is a mechanism on how like we combine the information from both modules plus the persistent module, but let's just set it aside for now, not to complicate the situation. So yeah, exactly. So the objective is, yes, we want to learn this based on using that loss function, and then I'm not so sure whether this WK then WV. My understanding is that this is the weights from the outer loop training um from the main like the core attention modules. But after I'm saying, yeah, the model learns how memories mapping between keys and files at test time. Okay, so yeah, so my understanding is that this the weights of the keys and values are the weights from the outer loop, from the attention modules, and then this becomes the as Peter mentioned, becomes the hyperparameters of the inner loop training. And then we optimize uh the the long-term memory during inner loop training. Okay, and the next bit is that then how the long-term memory module knows or what to for which information to forget, because we want to be able to have this memory management. um yeah, they have this extra mechanism for this that basically they didn't explain much more detail here, but my understanding is just it's incorporating this surprise and see like whether this is like something that we need to forget or not. But I feel like this is not very clear to me in this section. So if anyone like has more understanding on this, please jump ahead. But I'm going to skip that for now. Um.
I
Yeah.
I
Okay.
can give I can give a bit of an explanation. So
Yeah.
the way that they so this m at any given point, that's the weights of a neural network. And they add what they call like this gating mechanism, which is a value between 0 and 1. And so you can think of that as like the percentage of the network that you want to, the previous network you want to forget. So you could say, I have 100 facts, and alpha or A is 40, which means I'm only going to remember 60 of those facts because it's you're taking
Mhm.
a small. So that's the forgetting mechanism is literally just like taking whatever the weights are and making them some fraction of what they were, with the idea that this reduces the amount of information in the memory.
How would it be different from the surprise? I guess it's like if there is new information because it has high gradient, like it's a big surprise, then there is still this gating mechanism to tell whether, oh, this surprise is something good to keep or not. But how
Well,
would it
the
with that?
surprise is separate because the surprise it comes from the loss function, and so the gating mechanism doesn't actually touch its alpha doesn't touch S, which is what is the update, where the update is. It
Mm.
only changes M from the previous time step.
Yeah, okay. And alpha is something that the model learns.
Yep.
Yeah, yeah, okay. It's not hyperparameter. Yeah, okay. Cool. Okay, so then the next question is that what is the architectures of this long-term memory module? Here they mention that they only use like very simple architectures, which is a simple MLP with even we can use only one layer, so greater than or one layer. And they say it's not a fixed architectures, but the main contribution of this paper is like how this long-term memory, how can we have this separate long-term memory module that is trained during test time and how it uh, works with the other memory module, but they don't want to like really deep dive into what architectures that we should use for that long-term memory module. Uh, yeah, but they mentioned that with at least two layers are strictly more expressive than just linear models. Okay. Okay, now we have that memory model strain. And then the next question is that how do we obtain information from that like train long-term memory module? Um yes, basically it's like we just do this multiplication with the input. It's like it's the same concept like how my understanding the same concept on how we retrieve information in transformers, because the main block is still like transformers with like attention. So we multiply with the query, the weights query, which is trained during the outer loop or during the main core attention flows, and then from that the output of that, and we retrieve it from the long-term memory module. The next section is how to parallelize this training. The problem with that approach that they've been explaining here is that yeah, we can imagine like if it's like very sequential, then it will take forever to train, and then basically what can we do to speed it up? um I find this I find this section is really quite difficult to understand, but I feel like that the idea here is that they separate the sequence into different chunks, because like let's say we have one, like let's say the sequence is consists of 1,000 tokens. Without parallelization, basically it will require like its own complexity, so it has to be done like 1,000 times. And the idea is that they want to split this sequence into chunks. So if we split into like 10 chunks, so then it becomes like there will only be like 100 steps, something like that. So I will say it's not going to be completely parallelizable. It's just like parallelized to certain extent using this like chunks or like this, yeah, batch or these chunks, but it's not going to be like 100% parallelizable. And they simplify some terms here in the training that um, there are some parameters that actually really input dependent. So if we see here, like if we imagine we have a sequence, and then like I mean the first word of the sequence is like something, and then we want to use this first word as the input of the next, like as the input to know like what to generate in the next token, then we need to incorporate like the previous word. So that's why we are like very time dependent here. But if we want to parallelize this, then we cannot make it we cannot keep this complexity, because then how can we know this time dependent parameters when we like split it into chunks? So they make some assumption, like by simplifying it, that there are some parameters that are actually input dependent and become like make it same, something like that. So then, yeah, basically it will be easier to compute. Yeah, if we have time and anywhere Peter wants to dig more about this section, we can do it later. Now I think it's good to like move on, and then we can go back to dig deeper here. I don't want to be like be stuck here. Okay, and the next module, so we have the core main attention module, which is trained during uh mm, which is trained during like the training time only, and we call it as the outer loop. We have this long-term memory, which is trained during both training and inference time during inner loop. We also have this third module, which is the persistent memory. So this persistent memory again is input independent, because it basically contains the information of a particular task, so it doesn't need to be always updated when it receives like new information. That's why they call it persistent. And again, actually they didn't really deep dive more into it. uh Basically they mentioned that it's still something important to have, and it's just basically uh just like a softmax. Yeah, let's just like softmax operation with this the matrix of key. So wk is like the weights matrix that corresponds to the key. Wv is the weights of matrix that correspond to the values, and as we know, we have the third one, which is the weight matrix that corresponds to the query. So it's just basically the softmax between this key weight matrix with the input, and then times the weights that correspond the values. Um. Okay, so I think the last very important bit of the contribution of this paper is that how to incorporate this. So now we have this 3 different memory modules, and then the question is that how do they behave in action? How do we make use of these 3 different memory modules? They offer 3 different ways to do it. The first one is memory as a context. Second is the gated memory, and that one is memory as layer. So let's look into this. What is memory as context? So let's just look at the diagram. Okay, so the first way they mentioned is the memory as a context. That basically we have this neural long-term memory. We have the input sequence, and then when the input sequence like comes in, we retrieve information from the neural memory, uh, and then we concatenate this memory, this information from the neural memory to the sequence, and also we concatenate the information from the persistent memory. So if we see here the total context, like the total information here is basically concatenation of the original sequence, just like the input and the information retrieved from the neural memory as well as the persistent memory. And we pass this to the attention, the main core memory attention modules that basically will see, okay, like to attend of this context, like to see, what's uh the meaning of this. Yeah, like the how to say, like, yeah, the important information from this sequence. Yes, Evelyn?
So yeah, hey, I'm trying to understand this a little bit better. Is this basically like RAG, but you do the retrieval before the attention? Is this kind of how it works, or am I getting wrong?
Mm. I will say my understanding is that in terms of retrieval, it's kind of similar of RAG, but the I mean, because it's retrieving information from like a database or like a memory bank. But uh in this situation, like in this case, this neural memory is learnable. So it's always dynamic.
Yeah,
Um
I think that's a good point, Inneke, that maybe it's not exactly the same, but if RAG, if the vectors in your vector database were changed at test time, like based on the data that you were looking at, then it would be the same. It's
yeah,
pretty similar to that.
yeah. That's what I think. So yeah, thank you, Peter. And thank you, Evelyn, for the question. Uh um okay. After we retrieve this information and we pass attention to it, and then we update the neural memory. I cannot see the chats, so
Don't worry about it. It's another answer to the question that so we can keep going.
okay. So after this attention mechanism, we update the neural memory. So in my understanding, the idea of this attention is that, okay, we compress, like we want to find what is important information from this concatenated information, and we use that to update the long-term neural memory. So that's why like it learns during test time, and then we aggregate the information from this neural memory after it gets updated here with the attention, and that returns the output. I find it a bit confusing at first to think. So it's like during the test time, sorry, let's repeat again. During the training time, um, is it during training time actually? Like we concatenate like this information. I think this is more.
At training time, you don't do all of this stuff. At
Yeah,
training
I think
time,
this
it's
is test
just
time,
yeah, this
right?
is only test
Yeah,
time.
exactly. Yeah. So during test time, let's say the model sees like a sequence in sentences, it concatenates that sequence with the information from the long-term memory and also from the persistent memory. So we have like more like enriched information. We pass it to the attention, so the attention will sort of like know what are important information from this concatenated sequence, update the neural memory, and then concatenate, like aggregate um, the the output of the attention with the new retrieve information from the neural memory. This is my understanding. And then it returns the output. And that's what we call it as a context, because this long past memory, like it gives like more like richer information to this short term, like immediate information that attention processes. And the second way to incorporate the memory is what they call gated memory. So let's see the diagram. Okay. So in this gated memory, we don't concatenate the retrieve information from the long-term neural memory to the sequence. We only concatenate the information from the persistent memory and the sequence. And then this concatenated information between the persistent memory and the sequence is used to update the neural memory, as well as it's passed to the attention. And then the final output is basically the aggregation from the information retrieved from the neural memory based on this concatenated sequence with the attention. So it's slightly simpler in this case. And the last one, which is the memory as layer. Memory as layer. Where's this? Okay. So the last one, like there is not even aggregation between the information from the neural memory and the attention. So it's very linear. So this neural memory, as it is, like it behaves as a layer. So we concatenate the information from the persistent memory, and the incoming sequence retrieves the information from the long-term memory based on this sequence, and then pass it to attention. They mention here what are the benefits and the caveats of each option. So I think in general, like the first one, memory as a context, has like more like richer information. And the attention module here, it really helps to sort of like filter out what information that is important to update the neural memory. So that's the good thing of this. And this mechanism doesn't exist in the two other architectures. So yeah, that's the main thing. Yeah. I'm not sure it's really the caveat. Basically, when we go through this experimental results, like this memory as a context is the winner. Like mostly it is the best architectures in terms of performance among the other two. Okay, we can quickly have a look on the experiments. They use quite various tasks, which are language modeling, common sense reasoning, needle and haystack, which is basically retrieving information from like a long context and understanding, Diana modeling, and time series forecasting. And these are like 5 questions they used that help them to like evaluate the performance. How Titans compare to baselines, what's the actual context length of Titans, how do Titans scale with respect to context length, the depth of memory, and yeah, the contribution of each component, because we have like 3 different components. Okay. So language modeling, yeah, basically as I said, like mainly I mentioned that Titans outperform everything. In particular, the memory as a context architecture, it performs better with long dependencies. And memory as a layer is like the worst, which I think is expected. And this second task, needle in a haystack, yeah, basically the idea is that we want to retrieve information from a long, like small information from long text. And they compare like different sequence length. I wonder if they compared with TTT, but I wonder what is TTT. I think it's test time training module, this time training architectures. I'm not sure. Basically, so they mentioned that yeah, it's better than TTT to handle the memory capacity compared to Mamba to Mamba 2 has gating mechanism. Oh, this paper also mentioned that last architectures, which is like memory as a gate, memory as layers is the most common in other architectures. So I think that's why like they sort of like focus like the first architecture, which is the memory as a context, is the most innovative compared to the other two. Yeah, basically Titans have better memory management than this Mamba 2, which has forgetting mechanism. And another task is this Babylon. So basically it's to reason across facts distributed in extremely long documents. They fine-tune the memory as a context, and they claim that despite having much less number of parameters, then it still outperforms the competitors. Yeah, the next bit they experiment the effect of deep memory. But they mention yes, the model scales linearly with respect to context length, and then the training throughput as the function of sequence length, but like definitely there is a trade-off on this because with more depth then there will be like training will take longer time. Yeah, and in time series forecasting it performs all the other baselines, DNA modeling. LLM is the last one. Yeah, the last one that we did not is the fourth architectures that they didn't put much detail. So I don't think we need to focus more on that. So yeah, basically it. Yeah, it's similar to what Manny mentioned before. Like they claim they have better memory management here, even though the memory is slightly slower. So I think that's all. We have 4 minutes left. Yeah, any questions, any comments so far? What do you guys think about this paper? Do you think it's something very innovative and like the next trend?
So there's a comment that there's some
Oh,
unofficial code for the paper.
well, comments are in Mandarin.
So thank you. I think it's a really interesting paper, and I like the framing of it, the fact that they've tried to reframe attention and say attention really shouldn't really be called attention, it's this other thing. And so I think that's very useful insight from them. So that's the main thing I'm going to take away from this. And I think I might dig through the code and see if I can understand it at another level.
Yeah. Oh.
Can you hear me?
Yeah, sure.
Thank you very much. Did you notice in your studies that had anybody started implementing this? I just looked on papers with code and there's nothing there. So thank you, whoever put Dwayne. Thank you for putting that in there for the Chinese code. It can be probably fairly quickly translated. But have you seen Inneke or anybody else any actual implementations? Because this has been out a little while now, and I thought it was very exciting when it came out. Has anybody employed it yet that you've seen? No.
Inneke, so
Oh,
Have you seen anybody actually deploy it, turn it into anything yet?
I have no idea.
Okay. Okay.
I have no idea. I thought you were asking Dwayne because he found this. Yeah, I have no idea.
Okay. And I just thought you might have seen it on your travels. Sometimes you might have spotted that if somebody had deployed it. But it'd certainly be very interesting to see it. Does it actually work? That's what I would really like to know.
Yeah,
it's a tough
maybe
one
this.
because the models that they used for experiments were like less than 1 billion parameters. So it's hard to compare to, but they did get better performance than GPT-4 and 4.0 on stuff. So I don't
Yeah.
know. One big question for me, it's like I think that this would be really hard to, like, maybe it's not being deployed because at test time you have to train the model. So that means that you have to have a lot more infrastructure around your model when you're like every time you feed in a new sequence, you essentially have to train a model. And I could see maybe that does produce better results but why like a big company would probably shy away from looking into that as a solution.
Mm.
One thing I thought was they have a perspective on learning, which I thought was I disagree with, but their perspective on learning in the paper, it's like one at the near the start, is that learning is memorizing useful and accurate information about a task, and I actually think that's a simplification of what learning is, or like that there's a lot more to it because maybe you don't actually. Yeah, it's hard to say though. I don't know, but I thought I would bring it up just because yeah, it's not something I exactly agree with.
That comes back down to the room where someone's translating between two languages just via symbols and doesn't actually understand any of the symbols. Do they actually know what they're doing? And so most of our tests for humans, we ask them to explain, which is really, it really misses on AI models, whether they actually understand or not. Yeah.
Yeah, that's
It's different.
Searle's Chinese room. It gets us into very deep territory. It's fascinating, and I constantly go back and forth wondering whether it's important or not, because it gets you into questions of qualia and consciousness and all these kinds of things. Does AGI, does ASI actually need consciousness, qualia, and so forth? And I don't know the answer. I'm not convinced either way. I think probably 60% it probably doesn't. If it doesn't need these kinds of things, then we're going to get to AGI and ASI faster. But it's a huge question. And by the way, I think this directly relates, because one of the things that we humans do, which apparently we're conscious and we apparently have some intelligence, is that one of the things that we can do is we can learn on the fly. We can do, as it were, test time training. And I haven't had time to look into the neuroscience of how exactly we do it, but it's, we can do it, and to some extent other animals can do it. Probably ones with bigger brains can do it more. So that I do think is absolutely vital for AGI or ASI. So this is possibly a key, at least a step along the road, even if it's not the road, it's a step along the road in that direction. So it is actually extra fascinating in that way.
So maybe just one last question, at least for me, to Julian. Would you not consider in-context learning as learning on the fly?
No, not really, because it's just forgotten it. That's one of the whole things. ICL versus test time training is that test time training, you actually change the weights, and ICL, in context learning, you don't. So it's just forgotten it. You see what I mean? So I think that's a big difference.
That's fair. That's fair.
I've been going to a conference for the last 6-7 years called Artificial General Intelligence. And there it's quite clear that you need to break general artificial intelligence into several subcategories in order to answer Julian's question as to whether you need in-context learning and when you need it and when you don't. And so there's a lot of flux in the systems and the ideas people put forward based on when, how much, how general. Because a system that's general, if you make one that's twice as general, you can no longer use the term general. So how general, its definitions highly is the problem.
Dwayne, could you type the name of that conference that you go to into the chat,
Sure.
please? Oh, great. Thank you. Oh, right. Simple enough.
Well, since we're over time, I think we'll end it there. But thanks for sticking around and having a bit of a discussion about the paper. And Inneke, thanks for presenting. It's really interesting.
Yeah, thank you very much.
Thank you.
Thanks all. Thanks, Inneke.